Hey, this is Bill. I'm checking in with Paul McQuarter's Pico class. This is number 64. I can't believe we've completed 64 of these things. But anyways, this is pretty simplistic. He asked us to control a servo, and this is what I did. Run into weird things where the camera's not in sync with my voice. But anyways, I did the class servo, I did the init, and I did self, and I just did pin number. So there's only one thing going on here. From machine, import PNW pin. Then I did self pin number, and then you have to define the object, which is machine.pmw, machine.pin, then pin number up here. And then you have to set the frequency and the duty cycle. So I set the frequency here, and then I did the servo under the servo position is where I did the duty. So I called it servo pin 16. And then I defined it with as servo 1 equals servo 1 pin. And so we could actually make a bunch of objects here, servo 2, 3, whatever. In fact, maybe I should do that. Like I say, I saw some other homework examples where people were much more creative than what I did. Okay, so in the angle request, we're saying what is your desired servo angle, and this angle request is going to be passed up to the method here. So let's run this guy. How come it's not running? Oh, there we go. What is your desired servo angle from 0 to 180? You can see it's actually set at like 90, so I'll go 0, and it moves, and then the new angle is 180, and I'll do like 54. So anyways, that was my homework for this guy. Oh, and then also I kind of glossed over this. This calculation, look at homework or lesson 36, which he described, and he calculated this earlier using the frequency and milliseconds. And so he mathematically determined that 1638 and 8191 were the end points, the 0 and 180. And then this was just the math with the X and Y lines to make this 1638 to 18 or 8191 to make that scale fit the 0 to 180. Okay, I'm kind of backtracking here a little bit. This was actually homework number 63, and again, this is simplistic. I'm only passing up one thing, and I've seen other homework assignments where people are definitely getting more creative than I did, but I have to say thanks, Paul, because I've seen this kind of stuff along the way with people doing homeworks and really didn't know what they were talking about. Now I've got a pretty good glimpse into it. Paul did a rectangle, so I didn't want to do that, so I did round objects, and I did it as init, and all I do, just one variable, I pass it radius, and that's self.radius, and then I've got three methods under here. One is figures out circumference, and here is the formula for circumference. Radius is 2 pi r. Oh, I had to include math up here because I was doing the pi. And then it returns self-circumference. Then the next one I did was the circle area. And again, here's the calculation for that. Self.radius squared times pi r squared, that everybody knows. And then it returns circle area. And then I did the volume of a sphere of radius, whatever you ask for. And it's the same thing. It's 3 over 4 times the radius cubed times pi, and it returns a sphere volume. They did a float here. What is your round object radius? And I declared it here. My round object equals round object's passive radius. Print your most excellent radius is, and I just put units here because you're just putting it in. And if you were using inches, you could say, well, this is going to be inches. If you're using leagues or cubits or whatever, I just put units to be consistent that we need to do something like that. And it's going to return circumference and then the units. So hopefully it prints nice. And then I put this little caret for area is squared, and on here for volume, it's cubic volume. So what is your round object radius? We'll say 5 miles. And the circumference is 157, area 78.5, volume is 523 cubed. And then I kind of did another thing here, and the results are more interesting, I think, than the homework. But I kind of set something up here, and I'm calling the class Solar System. And then I've got all these, and you pass it the diameter of your Earth model. So the reason why I kind of did this is if you wanted to demonstrate the size of the solar system to somebody, you could take a basketball and, you know, drive a stake in the ground, call that the sun, and the basketball would be the scale of the Earth, and this would, you could determine how far away the Earth is from the sun or from other planets, and then it gets more interesting than that. But anyways, I did Mercury, Venus, Earth, Mars, Saturn, Uranus, Pluto, or where's, oh, Uranus, Neptune, did I say those? Pluto, I have to include Pluto because I'm old. And then, just for interest's sake, I threw in Alpha Centauri, which Paul can probably see because he's close enough to the equator, but it's in the southern hemisphere, one of the brightest stars. You know, actually the Southern Cross and Alpha Centauri that points to it, you know, the stars that make up those constellations are all within like the top dozen brightest stars in the sky, and there's a lot of stars in the sky. But anyways, Alpha Centauri is the closest sun to our sun. So it's our closest neighbor sun in the Milky Way galaxy. And then I decided to throw in Andromeda, which is the first regular galaxy, or the closest regular galaxy to our galaxy, the Milky Way. And, you know, if you look at the night sky, you know, there's this, what is our Messier 86 Markhan's chain, and you're looking at such a really small piece of the sky, and, you know, there are like a dozen galaxies. So, I mean, there's a bazooka of them out there. But anyways, like I say, I went through And a lot of this math here is really just converting stuff because I'm entering the model in inches, and then here I do different returns, and it actually, I wanted it to convert it to inches or feet or yards or miles, whichever one is the appropriate scale for what we're doing. And these numbers I just looked up. Well, I calculated actually. What I did was, in this example, I looked up how far away is Mercury from the sun. And then I looked up the diameter of the Earth. And so this is how many Earth diameters away it is. So that way I maintain the scale of whatever you pass it. And you can see I've got return in here multiple times because it'll just kick it out of there. And since I wanted miles or yards or feet or whatever in there, I returned Earth, comma, miles, and it prints out kind of weird, but whatever. Anyways, it works. But this is one of the more interesting things I saw in here, and I just Googled this just to do it. I looked up the diameter of a grain of sand, and they said that was 0.0196 inches. And so our Earth model is a grain of sand. And we hit this, and you can take a look. So it has how far Mercury would be from our sun. Okay, Earth, you can take a look. And the things expand so quickly. Inches is not even in the calculation here, but even with something as small as a grain of sand. But Earth is 6.4 yards away. Pluto is 254 yards away. So you guys are probably watching the Masters, and those guys are hitting 254-yard drives and beyond, but the average golfer doesn't, and so you can see that's quite a ways. But this is where it gets really interesting. Alpha Centauri, our closest star or sun to our sun, is 988 miles away, nearly 1,000 miles away, and our scale is the Earth, the size of a grain of sand. And that just amazes me. And then our closest galaxy, Andromeda, is 5.8, or, well, it's to the 8, so that's 58 million miles away based on that scale. And anyways, that just amazed me. That's it. I need to move on to the Arduino homework. Catch you later. Bye-bye.